this is pretty cool. First time that we've had something like this out in Denver. Been out to Denver quite a few times. I was actually out here last month for FOSS4G, the big geospatial open source conference. And I actually gave this presentation there. So if any of you guys were at FOSS4G out here in Denver last month, it's the same presentation. I added 2 more slides, but other than that, it's the same. I was pleasantly surprised at FOSS4G the number of Postgres users that were here. So there were 700 Postgres users here in Denver last month. It was pretty amazing being here. What I'm going to talk about is scaling Postgres using a product called Stado. It's an open source product that lets you scale Postgres beyond a single server. Starting off, who am I? I'm the founder of a company called Cirrus Technologies, focusing on consulting in the cloud space, mainly around databases in the cloud, moving people who have been in an enterprise data center into a cloud environment. Before that, I was the chief architect over at Enterprise DB. Spent a number of years adding Oracle compatibility to Postgres. So we've got a very deep understanding of the internals of Postgres. And I'm also the co-organizer of the New York City Postgres Users Group. So we have about 300 members there now, regular monthly meetings. I encourage you to do that, doing that here too. For you folks who are local here to Denver, there is a Denver Users Group. Start attending those meetings as they're there. It's a great community as you get in order to get to talk to other Postgres users month after month. It's a great way of doing it, and we've been doing it in New York for a couple of years now. So we'll talk about what Stado is, the architecture of it, kind of how it handles different queries, how it's scaled, and then most importantly, the limitations. I'm going to tell you all the really cool things about it, about how it'll scale, but I'll also tell you where it's going to fall down. So this way, if you have an application that doesn't quite work with it, you'll know it ahead of time instead of wasting all your time trying to. So what is it? It's really a continuation of the GridSQL project. GridSQL, and really the prior version of it, ExtendDB, has been around since really 2003. Enterprise DB acquired it back in 2007, I believe, and then open sourced it as GridSQL. So it's been around for a number of years. A little over a year ago, Enterprise DB stopped supporting it and just donated it out to the open source community. And when I left Enterprise DB, I picked it up and I renamed it Stado because of different trademark issues and things like that. What Stado means is just herd in Polish. Kind of like Slony means a group of elephants in Russian. I figured it was a nice way to name it in the Postgres world. So it's not a new project. It's been around for years and years and years. It just really has a new name. Essentially what it is a shared nothing distributed data architecture. It lets you take your Postgres database that runs on a single server and span that same database across many servers, or a single server and parallelize it across all the different cores you have on that single machine. It's essentially a layer that sits on top of Postgres that handles all the coordination for you. It's essentially an open source version of Greenplum, Netezza, or Teradata. It's really designed for data warehousing and reporting. What is it? From the beginning, it was designed for parallel query, where Postgres is, you have this great big query that's going to hit a terabyte worth of data, and you throw at it with a box with 16 cores, and you look at it, and one core is pegged, and the rest of them are sitting there doing nothing. This, from the beginning, was designed to parallelize that across all your cores and across multiple different machines from the beginning. It's not just a read-only scenario, but it is geared towards data warehousing. So it's not going to be able to keep up with your massive transaction load, but it can handle updates, deletes. It is transactional. But the ideal way of doing it is through parallel loading and data loading. So if you have bulk loads, it does that extremely quickly, and that's the way to really get data in there. You can do one insert at a time. It's going to be about 10th the speed as a regular Postgres instance. But if you bulk load it, it's going to be about 10 times as fast. And on the wire, it's going to look like a regular Postgres database. It sits on top of Postgres, but you can connect to it from PSQL, and it's going to look like a Postgres database to you, even though what you're connecting to is Stado sitting in front of 10 Postgres databases. So what isn't it? It's not a replication solution like Slony or Bocardo. It's not designed for a replication of any sort. It does do some replication in there, but that's just really a performance enhancement. It's not a high availability solution. It's not designed to give you 5 nines of uptime. It's not a scalable transactional thing like PostgreSQL. PostgreSQL doesn't have query parallelization. It's designed for massive number of concurrent writes and scaling that across a bunch of different servers. And it's not one of those elastic, NoSQL, eventually consistent databases. It is essentially an open source data warehousing solution. So what does it look like? Again, it's a loosely coupled share nothing architecture. So all these data nodes are Postgres databases. They're all sitting there, independent Postgres databases, and they don't talk to one another. Everything is coordinated through the central coordinator sitting on top of it, and there's agents running on each one of those Postgres databases. If you have to do some sort of row shipping across node joins, when you have data in one node that has to join to data in another node, and it does that, the agents speed that up. And it maintains everything through a couple different repositories. You're going to have the metadata repository sitting on the coordinator, and each one of those data nodes you could connect to that Postgres database with pSQL, and each one of them is going to have its own database. And in that database is going to have a subset of data. So in this scenario where there's 4 data nodes, each one of those nodes is going to have a quarter of the overall data. You got a terabyte worth of data, each one of them is going to have 250 gig. So the way you set it up is if you're going to have multiple cores and you want to be able to leverage multiple cores, the best way of doing that is to put multiple Postgres instances on each physical server. Because it's going to parallelize at that level. You can do it at the database level. It's much better to do it at the instance, the cluster level. Run multiple clusters. This will let you, when we get to the end of the presentation, of being able to scale out better as you want to add more nodes. Your tables are going to either be replicated or partitioned, and we'll get into a little bit more detail of what that is. I think that's why there's been a lot of confusion over the years of PostgreSQL or Stado being a replication solution, because it says tables can be replicated, but it's really just a performance enhancement. You want your replicated tables to be your relatively static lookup tables, state code, country code, things that you're always joining to but never updating. And then your partition tables are going to be large fact tables. So if you think of it as a star schema, you're going to have one large fact table and a bunch of dimensions around it. All those dimensions should be replicated, and your fact table should be partitioned. So this way, you'll be able to parallelize across everything and get linear performance. You could also leverage Postgres' internal partitioning mechanism. So say you have a really big sales table that you want to be able to partition across multiple servers, but you also want to partition it by month, so sales month or year. You're able to leverage the constraint exclusion partitioning inside of Postgres as well. Because whenever you could make a data file, and more importantly an index, smaller, do it, your queries are going to go faster. So if you could split it up, you might have 1 billion rows in a table, but you could essentially through this, if you're running 10 nodes on it, each one of them is going to be 100 gig, and then you run 10 partitions, each one of them is going to be 10 gig. That's a more manageable table size. So again, making things smaller makes things faster, which is what I just said. And because of the way Stado works, you're able to scan those partitions in parallel, which you can't do inside of native Postgres. So the way we do this is in the DDL, in order to create your tables, we've added a little bit of syntax at the end of saying state codes, for instance. You put the replicated syntax at the end of it, and that'll be stored in the metadata repository of Stado. And what that means is every one of the nodes, data nodes inside of Stado is going to have exactly the same copy of it. So if you're going to update this and there's 10 nodes, you're going to make 10 copies of it. But what you're going to do is all your queries are going to join to that. So you want that local to everything, and you're never going to change it. How often do we add states to the country? Right? It's a relatively rare thing, so it's not a big deal replicating that. For your tables that have all their data, so this is the Tiger data set that you get from the US government that has all the roads in the country. You have the additional syntax of a partitioning key. And here I'm just partitioning it on the surrogate key, GID, which will do a hash partitioning across all the different nodes and pretty well equally distributed across all the different nodes. You can partition it on any of your columns. I wouldn't advise you to do it on a geometry column because you have to calculate a hash in a geometry column. That's going to be extremely slow. But doing it on a surrogate key works really, really well. You could do it on state code, and then all of New Jersey is going to be here, all of Colorado is going to be here if you're going to join regularly on state code to other tables that you might also partition by state code. So the way Stado gets all the performance enhancement gains, it really is through its own optimizer. So it's sitting on top of Postgres, and it has its own parser, it has its own optimizer. So when you send in a query, select star from foo, it's going to parse that and then also optimize it. So select star from foo knows it's going to have to get all the data from all the nodes. When it's going through its optimization, it does a cost-based optimizer the same way that Postgres does. But what it does is it calculates the most expensive thing inside of Stado is row shipping. So you have to join two tables that are on different physical nodes, and you have to ship all the million rows from one server to another. That's a really expensive operation. So it tries to avoid that wherever possible. And it's going to look for joins to replicated tables, because if it's a replicated table, it knows it's on all the different nodes. You could join there. It knows for sure it never has to do any row shipping. And it's also going to look for joins on foreign keys that it knows are on the same table. So say you have a sales order header and a sales order detail, where you're going to, if you partition by sales ID and sales line ID, that wouldn't necessarily mean that all the sales order numbers are all on the same physical server, so it has to do row shipping. If you partition by sales order number on everything, you could guarantee that everything's on the same server with a foreign key, and it's going to choose that plan over something that'll do row shipping. The other really big performance enhancement it does is through aggregation, doing aggregations in parallel. And it does that by splitting up the aggregates really into two phases. So if you have all your data out on all the different nodes and you want to do an average, what Stado doesn't send down average to all the different nodes. What it does is it says, give me the sum and give me the counts of that particular column. And then on the coordinator, before it goes back to the user, it's going to sum the sums, sum the counts, and do the division in order to give you back the average. So this way, you're able to calculate all that stuff in parallel, all down on the data nodes, and you're not bringing back all the data to the coordinator and letting it do all the calculations at the end and essentially becoming a bottleneck. So this way, all that stuff happens in parallel. So this way, you're able to scale linearly. So now let's actually start looking at a little bit of queries. Again, this is using the Tiger data set. It gave me a nice 250 gig worth of data. And what this simple query does is it just sums up the lengths of all the roads in the US that are interstates. If you're familiar with how long it should be, this is really probably about twice as long as it's supposed to be because the Tiger data set is at the county level and some of those roads go right along the county borders. But this is a perfect example of a nice simple query that's going to do a sequential scan across all the rows in the table and sum up all the lengths. What do we get? So if I run this on a single server, I ran this on an Amazon EC2 instance, one of the small instances, which had about 1.7 gig of memory in it. On one instance, it ran in 101 seconds. On four nodes, it ran on 25 seconds. And when I scaled it out to actually running it on 16 EC2 instances and parallelized it across all 16 instances, it ran in 4.8 seconds. So it is fairly linear. And if you notice, right around 12 nodes there, it actually is a little bit faster in linear scalability. And the difference there is that at that point in time, all the data that it actually needs is in cache, so it never has to hit disk. So because you're adding 12 nodes, I had 12 times 1.7 gig worth of memory in order to be able to do that, so it never had to hit disk. So you're not only able to scale CPUs, you're also able to scale how much cache you have in your overall system. So that's a pretty simple scenario. You'd be able to take that and do that, just script it and be able to parallelize it across a bunch of different nodes and be able to return back the results. But if you had a more complicated query of this one here, of taking that same row table and joining it with some census data, and also joining it with the state codes table and the country code table. And what I'm looking for is give me the top 20 counties in the country that has the biggest density of population per kilometer of road. which one are the most densely populated, which would kind of translate into which counties have the biggest traffic problems. If you had a more real-world scenario where in this thing we have some sub-selects, we're doing some joins, we got an order by, and we got a limit of 20 on there. So it's a more complicated query, right? So it's not just a simple sum. So as you'd expect, top of the list, New York got 1,049 people per kilometer of road, and everything's kind of concentrated in the Northeast. You get some interesting things in there that Hawaii and Puerto Rico pop up in there, right? They're islands, I guess things are a little more densely populated around there. But it's more detailed analysis, right? And when you're joining together two tables that have millions upon millions of rows, right? And if you're running it on that one instance, when I ran it on one instance, it took 3,900 seconds, which was about 66 minutes. As I scaled that out and added more and more nodes, when I got it out to 16 nodes, it ran in 282 seconds, which is under 5 minutes. So by scaling from a single instance of Postgres on a single node against that giant data set, again, using a complicated query, and scaling that out to actually 16 cloud instances, this will run on physical hardware or clouds, I was able to save over an hour's worth of time running that single query. And we see this time and time again for using Stado. If you want to go, if I wanted to get that cut in half down to 2 minutes, I'll just go to 32 nodes. Based on that query, it is linear scalable. You add more nodes. You want to go faster, you add more nodes. And it's really there for detailed analytics like that query that I just showed you. And it does work across an entire set of different analytical queries. This was done against the DBT3 several years ago, and it ran across the entire 22 query set. And as you add more nodes, it goes faster. That's the idea of it. If you want to be able to guarantee to your users that you could run a particular query in a minute, you run it on 1, you run it on 4, you could see what the scalability is, and you can easily calculate how many nodes you need in order to get that query done in a minute. So now I told you all the cool stuff about how you could run things from 66 minutes down to 5 minutes. I'll tell you what it doesn't do. Because it has its own optimizer and parser, it doesn't have everything that native Postgres has. So it doesn't, as Postgres adds more features to it, we have to also add it to Stado into its own parser and optimizer to take advantage of it. And we haven't added things like windowing functions yet. You can't run stored procedures. If you do a create function on there, it's not going to work. There's kind of workarounds for that, but essentially everything comes in as a SQL statement. There's no full text search. Right? Before the latest release of Stado, there was no geospatial support. We saw a big need for geospatial support because geospatial queries are very CPU intensive and would take advantage of the parallelization extremely well. So we'll be adding more and more features over the course of time. And if there's specific things you need, let us know. But it's not going to be full native Postgres. If not everything's going to work because it has its own parser. And transaction performance. If you're sending things in as a single insert or update at a time, especially if you're going to update something that it's partitioned by, where it has to kind of delete it from one node and insert it into another, it's going to be slow. You're always going to have to do is do an additional network round trip because everything's going to come in through the coordinator and then send it out to a data node and then all the way back to the user. The partition stuff also has to calculate the hash on whatever you're partitioning by. So it's going to have to do an extra amount of CPU cycles on the coordinator in order to partition rows. And the replication, it's going to have to commit to all the different data nodes before it's going to return back a success. Which again is, if you have to get data in, bulk load it. You could use the copy command. You could use GSLoader, which will parallelize things really well for you from the client. It's actually a pretty cool way if you have some bad records in there. It does some handling of bad records. So this way, you import a million rows and one of them is bad, it's not going to roll them all back. High availability. There is none. Right? If one of your data nodes goes down, you're down. There's nothing in the coordinator saying that if one of your nodes is down, fail over somewhere else. Or just ignore that part and return back an error of something that wouldn't touch that particular data node anyway. So what you have to do is configure high availability on each of the individual nodes. So if you have 10 nodes inside your Stado cluster, you have to set up replication or something on each one of those. What you could do is use each one of those data nodes as a failover of another one. So essentially you're setting up RAID at the server level. So this way they all fail over to one another. If one of them goes down, one of those nodes might be doing double duty. Also, getting a consistent backup across all of them is a little difficult. So if you're actively putting in transactions, there's nothing inside of Stado saying pause. There's no PG start backup at this whole Stado level, which will send it down to everybody. Essentially what you want to do is pause the coordinator for a second and then do a PG start backup across all your data nodes and start it back up again. And then you could get a consistent backup. You could use a bunch of different tools, whether it be OmniPitter or whatever, in order to get those backups at the bottom level. But you have to handle that yourself. You're essentially going to be managing 10 Postgres databases. You have to coordinate the backups of it. So again, there's no way of ensuring that there's no transactions happening. Adding nodes requires downtime. If you want to go from 10 nodes to 20 nodes, you have to bring everything down. And essentially what you have to do is repartition all your data. So you have to export all your data out and then import it all back in. So this way it's repartitioned across all 20 nodes. Because your partitioning algorithm already spread out the data for the 10 nodes. What we do really is some advanced planning. Because most of the times when we're deploying Stado, it's usually on a very big database. It's on something that's in the multi-terabyte range, that exporting all your data out and importing it back in might take a week. It's not something that you really want to do all the time. So if you set it up in the beginning thinking that, all right, I'm going to start with 4 nodes today, but I'm going to go to 20 nodes in the future. What you do in the beginning is set up 5 Postgres instances on each one of those 4 physical servers. So this way, everything in the beginning is already partitioned for 20 nodes. When you want to go from 4 to 8, what you do is you bring everything down and just rsync your different databases over to the other one. So this way, everything's repartitioned, repoint the IP addresses, start them back up again. So this way, you don't have to repartition everything. You're essentially just moving the database themselves. You could do that through streaming replication or something else where you could replicate it over to the new nodes so your downtime's minimized. And also, by doing that in the early days, you're also being able to leverage multiple cores on the physical servers themselves. So, in summary, you can get really, really good performance out of doing it as you add nodes. It does scale linearly. As long as you're not doing the cross-node joins, you're going to see linear scalability. So if you have a classic star schema, you're never going to do a cross-node join. You're going to get linear scalability. We've tried it up to like 32, 64. I think we've done 64 nodes and seen linear scalability. Theoretically, it'll go faster. We just got tired of trying more and more nodes. This is entirely open source. If you don't like it, submit a patch. If there's something you don't like, we'll take submissions. More than happy to. It's all entirely written in Java. If you're a Java developer, know anybody that's a Java developer, you want to add a feature, more than happy to take it. So where do you get it? Go to stado.us. That's where you can download it. And if you have any questions, feel free to send me off an email or hit me on Twitter. And again, I'm pimping out the Postgres users groups. Get active in them here.